Tonight we welcome from Queen's University Belfast Professor Chris Watson, who is the Professor of Exoplanets and Low Mass Stars. Prior to moving to Belfast in 2008, he spent almost 10 years at Sheffield University, where he earned a PhD and held fellowships and postdoctoral positions. He oversees the Exoplanet Group and is currently the Deputy Head of the School of Mathematics and Physics at Queen's University Belfast. He has authored more than 160 scientific papers, and his research focuses on the identification and characterization of exoplanets, particularly the exploration of their atmospheres. One of the highlights was the weighing of Kepler 78b, at the time the smallest exoplanet known. This was a hellish lava world equivalent in size and mass to the Earth, but with an orbital period of just over 8 hours. Building on this work, he is now pushing to develop techniques that will allow true Earth-like planets to be discovered in the future. Can we give a big Mexborough and Swinton Astronomical Society welcome to Professor Chris Watson.
Thank you very much. Shall I share my screen?
Yes, please.
Yep, just give me a moment. And that will share, and then I forget that to play. Hopefully you should all see a nice fancy screen there. And I just want to also thank you very much for Ian for the thumbs up. If you could also give me thumbs up if you can see my mouse, just to give me an idea.
Yeah.
Brilliant. Fantastic, because that might be useful. So I'm actually not going to talk too much about the actual science and research that I do, but I thought something a little bit softer, which is talking about habitability beyond our solar system. So as was just said, I deal in finding extrasolar planets around other planets around other stars. But the ultimate aim for that really is to find what we would call an Earth analog, so a planet around a sun-like star in an Earth-like orbit, and something that we would recognise as being similar to the Earth. So that's the ultimate goal. I could talk a lot about the kind of techniques and challenges of that, but what is the reason why I'm after this? Well, ultimately, we would like to probe the question of, okay, where might we find life and other habitable areas? Oh, hopefully, yeah, there we go. Sorry, sometimes clicking different things, it depends what's going on whether you move on a slide. So here's this an example of something. This is 2016 from the BBC News, and many of you are aware of the Kepler, NASA's Kepler mission that's found thousands of at least candidate planets. The Kepler telescope discovers 100 Earth-sized planets, and then there's this beautiful artist's impression, and it looks quite nice. It's probably got beaches, and it's got the sea, and it looks kind of Spanish, it's lovely. But the kind of bit to be wary of here is that, yeah, Earth-sized planets, but just talking about Kepler 78, which was one of the discoveries I was involved with, which is a Kepler planet, that was Earth-sized, that was Earth mass, and therefore had an Earth density, so it was a rocky world, but it had an 8-hour orbital period compared to our 1-year period. Okay, so why was it a level world? Because its surface temperature is about 2000 Kelvin. Okay, lava is 1700 Kelvin. So a lot of these things you might see 100 Earth-sized planets, whoa, amazing. Okay, but they are still very, very different from our Earth, and obviously are not places where you would really go and look for a habitable world. So when we're talking about habitability, there's lots of terms I really don't like. So the Americans would refer to the habitable zone. So by this is the definition of in a range distance from the star, for example, where you'll have liquid water. Some astrophysicists will say habitable zone. I don't like that. Just because you've got liquid water, or may be in a zone where you have liquid water, doesn't mean it's habitable or has water at all. Americans would call it Goldilocks zone. actually don't know what Goldilocks has got to do with it. I don't recall there being porridge and bears involved in the science of this. I actually like to call it the kind of temperate zone, but whatever you call it, okay, what does that actually look like, and how do we define that habitable zone? And that's going to be the first part of my talk, is how do we define the habitable zone? And what you'll see is defining habitability or potential habitability is really, really challenging. So I'm going to give you a little bit of health warning. In this talk, I am going to start out with a bit of maths. Don't worry if I lose you, as long as you get the concepts, but I'm going to challenge you with that bit of maths. And that bit of the maths relates to this concept of the classical habitable zone. Okay, so how do I go out, I find a planet, I look at the type of star it is, I look at the orbital conditions of that planet, and then make a guesstimate, if you like, of where it, whether it lies in the temperate zone or whether it could have liquid water. And what we'll do is we'll go through the maths of that. You'll see the assumptions that are made, and then we'll apply it to our own solar system. But in this context, this is a plot of, basically, this is mass of star in solar masses. So one relates to a star that has the same mass as the sun, so this is a solar-like star. And you go down here, M dwarfs, these are red dwarfs. If you go more massive, you have more luminous stars. And this is distance in astronomical units. So up here we have the Earth at 1 AU around a 1 solar mass star. Okay, that's us. And in this calculation of the classical habitable zone, that's this yellow range here. This is where you, in this particular calculation, you can have liquid water. And in this case, the Earth sits quite nicely in it. And Venus is off to one side, Mars is quite close. The interesting things you'll see is by the time you're these hotter stars are more luminous. So if you double the mass of a star, you'll be 248 times as luminous, roughly. And what that does is means you've got a lot more energy, and that moves the habitable zone further away from the star. By the time you drop down here, so this is about 1/10 of a solar mass, so this is a cool, dim red dwarf. These orbital distances, you're looking at planets that might have orbital periods of a week. Okay, so you can be in a very tight configuration with your red dwarf star in this case, but have potentially the correct temperatures to have liquid water. And in here is something I'll talk about a little bit later. This dotted line is what we call tidal lock radius. Basically, inside on the left of this line, we expect the planets to rotate at with the same period as the orbit. So much like the moon is tidally locked to the Earth, so you've got the one side of the moon is always facing the Earth. In this case, you would have a permanent day side and a permanent night side. Okay, it's all kind of tides that are raised by the star on the planet, causes the orbital period and the rotation period of that planet to lock. Mars is a bit weird. Mars has relativistic effects, so although technically in our solar system it should be tidally locked, there is relativity going on at play there, so it's a bit weird. But this tidal locking could also influence habitability, and we'll touch on that later. So I'm going to start with my health warning. This is the one bit of maths I'm going to give you. And if I lose you, just think about the context. But I want to show you at the end of this, you could go off and you could calculate for any given star what the likely temperature is, okay, whether it lies in the habitable zone. I just want to show you what I would do if I found a planet around a star. So here's my planet on the right, here's my star, not to scale, obviously. And my star has a luminosity L. Just going to call it L. Okay, pop in some maths. So this is the total energy output, if you like, from that star. Okay, how bright the thing is. And what happens is, as that light propagates out to the planet, that light is spread over increasing spheres, if you like. Okay, so what you can see here is by the time we're out to that planet, that luminosity is spread over a much larger surface area. Okay, a much bigger sphere, if you like. So what we can calculate then is this. This is my maths beginning. Don't worry about it, because keep with the concepts if you don't follow the maths. Okay, so this is flux. So that's the energy imparted per unit area meter squared, for example, on my planet. That's given by the luminosity divided by the surface area of this sphere. And A here is the orbital separation from my star to my planet. So you can look this up in Google. You can say, what's the surface area of a sphere? Okay, and you'll find it's 4 pi times the radius of that sphere squared. Well, the radius in this case is the orbital separation. And that gives me my flux per unit area at the position of my planet. So here's my planet. I've got flux per unit area. So I can chop my planet up into lots and lots of areas. So basically I'm saying, well, how much energy is my planet actually going to intercept? And the planet, relative to the star, from the perspective of the star, just looks like a circle, a circular disk. So in each one of these kind of areas you've got here, you get this amount of flux depending on the the stellar luminosity and the orbital separation. So, and I have to change this a little bit. So what you actually have is our power input into my planet is that flux per unit area, this thing over the left, times the area that that planet intercepts. That's my flux, okay? What we had before, luminosity divided by 4 pi a squared, and the area of a circle is pi r squared. You can look that up in Google if you want. In this case, the radius is the radius of the planet. So that's my input power. That's how much power, how much energy from the star that the planet actually intercepts. Except, of course, you know, you go out there, it's cloudy. Clouds are quite nice and shiny and reflect some of that energy back into space. The polar caps of the Earth, for example, also quite reflective, white and reflective. So that reflects stuff back into space, even the oceans. So the Earth is reflective. So we take that input power, which is that flux, times the area that the planet is intercepted. And what we've got here is we multiply by a term that includes that reflectivity. So this big A is called albedo. So if A is 0, the albedo is 0, that's a completely dark planet. It absorbs all the light that comes in, and this whole thing just goes to the flux times the area of the planet. Okay. If it was a perfectly reflecting mirror, albedo would be 1. This would equal 0. Input power is 0 because all the light gets reflected back into space. So for the Earth, the albedo is about 0.3. So the Earth reflects about 30% of the light back into space. So that's my input power. Okay, that's what I would do. So I've got my input power coming in, my flux coming in, a bit of it scattered or reflected back into space. And then it depends on the area of my planet that's intercepted from that star. So that's my input power. But what goes in must come out. Okay, so I'm kind of doing a balance. So that input power is then re-radiated as heat. Okay, so I can balance this input power by an output power because what's left over is re-radiated by heat, and that ultimately escapes into space. This is my output power. So what I've got here now, we're nearly through the maths, everyone, bear with me. But what we've got here is, imagine we take that input power, that light, and we've spread it now over the whole surface of my planet. So remember we had 4 pi a squared earlier. It was the surface of the big sphere that the light from the star was distributed around. Now this is just the radius of the planet. So we're distributing that flux over the total surface of the planet because the surface, the Earth is rotating. Okay, and then this is very famous. This is a black body. It relates flux to temperature. So this sigma is a known constant. You can look that up in Google, and this temperature is in Kelvin, so this is temperature to the power of 4. Okay, and what you can do is you balance the input power to the output power. We did the maths for this. You can do a bit of matching. What look the same? Well, what you actually find is the radius of the planet disappears. So the radius of the planet, the size of the planet, has nothing to do with this calculation. It just disappears because it cancels on both sides. So I'm left with luminosity of my star. Astrophysicists know that very well. We can go off, look at the star, we know that. We can measure the orbital separation. We may not always be able to measure the planetary radius because we may not be able to see it, okay, but we don't have to. We might not know the albedo, but we could assume, for example, it's the Earth's albedo, 0.3, or we could put in a range of reflectivities to get a span on things, of temperatures. We know this, we know what the number 4 is, and that just leaves the temperature. So you can rearrange all this, and this is basically what we do. Okay, so we've made those assumptions. We've got some measurables. Okay, we know that the radius planet doesn't really figure, and we just say, right, it intercepts so much energy from my star. Some of it is reflected back out, and it depends on the distance between the star and the planet, and then I can get my temperature. Okay, and this is something that we call the equilibrium temperature of the planet, and it's the kind of thing that I would calculate. If I found a planet, I would go off and I would calculate this. Okay, so let's apply this to our solar system. Okay, so you can see, you know, there's a bit of maths rigor behind that, and hopefully you agree with the kind of concept of this. So let's go and apply that to the solar system. I know the luminosity of the sun, I know the orbital separation of these planets, I even know their albedos. And up here, the temperatures that I get, I've got in degrees centigrade because we all kind of realize this, you know, understand degrees centigrade quite well. So Mercury, you would calculate 136 degrees centigrade, okay? So roughly the temperature of Heathrow 2 weeks ago. A joke. But Venus, 31 degrees centigrade. Earth, in actual fact, lies outside the classical habitable zone. Okay, so if I was looking back at the solar system, Venus would be the planet I'd be most interested in terms of habitability. I'd be interested in Earth, but it wouldn't be as good. Okay, and Mars here is at minus 67 degrees centigrade. Well, the real temperatures are down here at the bottom. So Mercury is between 430 degrees centigrade and minus 180. Well, if you split the difference, you get this. And that's basically because Mercury doesn't have an atmosphere, so you've got basically really hot day side, and you've got a really cool dark side. But if you average that temperature across the surface, you pretty much are around about 136 degrees centigrade. So it works really quite well for Mercury. Venus, woohoo, we're totally off. Venus is up at 400 odd degrees centigrade. The Earth, we're not too far off, but it's a little bit warmer. And we're a wee bit off on Mars as well. We think Mars is a little bit warmer than it ought to be in this. But you can see, even taking this, applying it to the solar system, where we've got well-known quantities, we get it very badly wrong in some cases. You know, we would be looking at Venus going, oh, that looks really nice place to have a holiday. Terrible. Okay. You don't want to be stood in that, as I'm sure you're all aware. So what went wrong? Well, of course, you know that Venus and lesser so Earth have the greenhouse effect. So the light comes in, yep, some of it's reflected, but as the sunlight comes in, when it's re-radiated, it's infrared radiation. This is where things break down, because instead of all of that energy being re-radiated back into space, it's absorbed by greenhouse gases, which then radiates back down to Earth again. So it acts as a nice thermal blanket. And that was something that we didn't include in those equations earlier. We just assume it's free to escape, which is why it works quite well for Mercury, because there's no atmosphere holding that in. And that's why it goes really badly wrong for Venus, which has a really thick atmosphere as well as the Earth. So the modern day habitable zones goes away from this classical habitable zone definition, where now you'll see this is an orbital separation. If you remember that first plot where outlaid the habitable zone, it's now effective stellar flux. And here, this is basically one relates to, it's the same amount of light as the Earth receives from the sun. So it's scaled to that. You know, here, it receives twice as much energy as the Earth does. Here, it receives half as much. So that's why the Earth is sat here at 1. And you can fuzzy up this kind of boundary. So if you have maximum greenhouse, which maybe you can see this, but this says maximum greenhouse, you can push the habitable zone right out beyond Mars. Okay, so that's why we think maybe Mars had a a maximum greenhouse early on in its evolution, and therefore sat in the habitable zone. It's lost its atmosphere and now lies outside the habitable zone. From another perspective, you can put in big reflective clouds, okay, and reflect a lot more light out than the Earth does. And that means you can then move your planets closer in to the star, because you're basically blocking a lot of that energy out. You can fuzzy up that boundary as well. So now the modern day definitions of habitable zones, I prefer to call them temperate zones, take into account different models of greenhouse gases, different atmospheres, and become a lot more complicated in dealing with that. But you saw how I was there able to fuzzy out those boundaries and make my planet more cloudy and reflective, and push the temperate zone much closer to the host star, or I can give it really thick, moist, or maximum greenhouse, and push the habitable or temperate zone much further away. You can start doing all sorts of things. So this is a bit of work that was done by Sarah Seeger. I think it was about 7 years ago, and then I saw it pop up again in the news fairly recently, which is where you can have essentially a planet with a big hydrogen atmosphere. We know these things exist. We know that there's these things called super Earths that sit between Uranus and Neptune and the Earth in terms of their size, that we believe have these really thick hydrogen atmospheres. At least some of them do. And hydrogen is a greenhouse gas. Okay, and it's very, very good at it. So this study was showing if you actually have a hydrogen atmosphere, you can push out the habitable zone beyond Earth, beyond Mars, beyond Jupiter, beyond Saturn, beyond Neptune. You can even have a free floating planet, a planet with no star, that potentially is warm enough to host liquid water. What you need is an internal heat resource. We have that on Earth. You see the volcanoes. That's radioactive isotopes generating energy to keep our core warm. And then you can enshroud that in a hydrogen atmosphere. And you can actually have planets without any stars. Okay, so free floating planet that could have liquid water on it. So this was some of the kind of headlines that came out. A large planet with a hydrogen-rich atmosphere could therefore conceivably trap, and I love how they worded this, a goodly amount of heat, which is a strange terminology. Okay, a goodly enough amount of heat, possibly enough to warm the surface of the planet to allow for liquid water. Okay, even if it was a rogue, or what we call a free-floating planet, a planet that orbits no star. And then someone noticed, okay, if you've got hydrogen, obviously that kind of life might struggle as soon as they discover fire, since hydrogen tends not to go well with fire, or cigarettes, or smoking, or anything like that. Okay, so you can see here that you can really, really, really fuzzy up your definition of what planet might be habitable or not. And it's kind of a big warning here. And that is only based on definition of having liquid water. Other people might rock up and say, well, maybe you don't need liquid water. Okay, so you can see how fuzzy it can be. Moving from that, there's another kind of concept, which is maybe there are different bits of the galaxy that will preferentially would be preferential locations in the galaxy for habitable life as well. So one thing that we believe happens in order to form planets is that we have a kind of a process on the left where you build small blocks, okay, little pebbles, little rocks, little boulders, and you get them either to stick together or collide together and then stick, and you build up bigger and bigger planets until you get to this kind of point where you have maybe like a Mars object, it's being pummeled, and we think the Earth got hit by a Mars, probably like a Mars-sized planet at some point, perhaps formed the moon. But you have these collisions of rocky bodies. Okay, in order to have rock, you've got to have heavy elements. So astronomers regard anything heavier than helium as a metal. So the only two things to an astronomer that isn't metal are hydrogen and helium. Everything else we say is a metal. Okay, and at the very start of the universe, of course, the Big Bang, there was only hydrogen and helium, smattering of lithium. Okay, but it was predominantly hydrogen and helium. You're not going to build a planet like our Earth from just hydrogen and helium. Okay, you need these heavier elements in there as well. So you have this kind of process of right at the beginning of the universe, quite possibly you didn't have any planets forming. You had the stars forming purely from hydrogen and helium. There's potential you could have really massive planets with a slightly different formation mechanism purely from hydrogen and helium, but they're not going to have a solid surface. So they're probably not going to be a good place for life because they can't kind of walk around and so on. So many of you will know that during the kind of lifetime of a star, if you have a particularly massive star, that will turn into a red supergiant, and then it will go supernovae. And in that supernova, which is a big thermonuclear explosion, that's when you generate all the heavy elements that then get distributed. All the gold on Earth comes from a supernovae. You do build heavier elements in this route, so the sun will become a red giant, or a planetary nebula. In that phase, largely it's hydrogen and helium that is released into the universe. The white dwarf has carbon, nitrogen, oxygen, silicon, and so on, but it's basically all tied up in that white dwarf. It doesn't get distributed and blown across the universe. So what you have here is you basically have a great recycling mechanism where you'll form something from the interstellar medium, from gas. You'll have high mass stars. They'll produce supernovae, and that releases heavy elements back into the interstellar medium. So basically you pollute the universe with increasingly larger amounts of these heavy elements that you can then go off and try and build a planet from. Okay, so if you do that, if you have a look at our galaxy, different bits of the galaxy have different ages. So the center of our galaxy formed first. So you've got the old stars there. They're the metal poor ones. Okay, so they formed when the very first generation of stars would have formed with no metals in them. So you can't really build planets. Then some of them die, supernovae, enrich slightly the surrounding area in metals, then you can maybe start building planets, and subsequent generations of stars have more and more in order to then presumably be able to build planets. So you can go and test this, okay, because we found planets, and planets and stars basically form from the same material. So we can go and, although we can't really probe the composition of the planets, we can take a spectrum of a star and we can say, okay, how much metals has that star got? Okay, is it metal rich or is it metal poor? So this diagram here, I just have to shrink a window. So this diagram here on the right, Fe over H, Fe is iron and this is hydrogen. So this is iron to hydrogen. And 0 here is basically, it's got the same metal pollution, if you like, as the sun. Okay, so 0 is the sun. So the sun lies here. Everything to the right of 0, so the positive numbers, these are richer in metals than the sun. And everything on the left, I'll call these metal rich, and everything on the left is metal poor. And what we actually have here is, in the dark colors, the blues are the metallicities of the stars which have known planets around them. Okay, so this, hopefully you see this in the blue, and in the reddy pink are the metallicities of stars where we haven't found planets. Doesn't mean there aren't planets there, but we haven't found planets at the very least. And what you see is, in actual fact, the metal-rich stars have the planets, whereas these stars that don't have planets are predominantly metal poor. Okay, so down here, all the stars that are really metal poor, we haven't found planets around them. Okay, and the sun, interestingly, kind of sits middle here, where it's probably kind of 50-50, whether if you go and have a look at a star like our sun, in terms of how much metals it has, whether or not you're going to find planets there. So this kind of ties on to that. Yes, you need these kind of metals, these heavier elements to build the planets. And where you have a dearth of metals or less metals or heavy elements, you're not finding that many planets, or at least you have a decrease in probability of finding planets. But we can tie that. You might say, okay, heavy metal rules. Okay, we want to look at objects. We want to have a look at bits of the galaxy where you're looking at, several generations of stars that have been polluted with lots of metals from previous supernovae. But your other problem is that a lot of these stars that I showed you where we find these planets, we're finding these kind of things that this artist's impression gives you, really massive planets that are in short orbital periods. So these are the hot Jupiters that you see. So Jupiter, we know in our solar system, tried to migrate inwards. It's a whole other talk that I can give you. Fortunately, it stopped at one point, but we find probably about kind of 1 or 2% of stars will have a hot Jupiter in like 2-3 day orbital periods. They migrated in. They weren't born there. They formed further out and migrated in. And if they do that, then you might imagine if Jupiter rolled through the inner solar system, it would probably destroy, chuck out the Earth, Venus, Mercury. You might have even seen kind of in the news that someone's come up with a study that even if Neptune changes its orbit by like 0.1% or something, that scatters Venus out of the solar system. Okay, so what we actually see is if you go too metal rich, you preferentially form these bad boys, and that might actually hurt your inner planetary system. So you have to be a little bit careful. You want something that has the right amount of metals, not too metal rich. Otherwise, you might end up with the wrong type of planets, not too metal poor. Otherwise, you might not form a planet. You want to avoid these things, supernovae going off as well, because life doesn't work well from that. So here's a plot in the galaxy of where we think the galactic habitable zone might be. So I'll talk through this plot. This is the health warning. This is the second tricky bit of this talk, and probably the last tricky bit of this talk. So what I've got here is time going back. Okay, so this is time now. So this is stars that form now. Would they be kind of in the habitable zone going back to when our galaxy formed? And then here is basically on this axis, this is the center of the galaxy, and we're going out to the outskirts. So what we see is we go back in time and we find this kind of region in blue. Everything's too metal poor. Okay, we're looking at the very first generation or early generations of stars, and they've not been polluted by the supernovae. If you go into the center of our galaxy, you've got lots of star formation and lots of massive stars being formed that then produce supernovae. That's great for producing the metals that we need, but it's not great for life because the supernovae will go and blat life. Okay, massive explosions and basically wipe out any life. So if you're too close, if you're trying to form something or you're too close to the center of the galaxy, when there's lots of star formation early on in the galaxy's history, you don't want to be here because you're going to get hit by a big bang. Okay, and you might not form planets anyway because you're too metal poor. As you go further out, you've got more and more supernovae that are going on. They die off. Eventually, we're not making that many massive stars due to the evolution, the way that the galaxy's evolved. But right in the inner regions where you've had lots and lots of, or quite a lot of generations of stars, maybe you make things that are too metal rich. Then up here in the gray, if you go kind of like 2-3 billion years, up here, maybe you've had too little time to form complex life forms here. So just not enough time here. And you end up with this kind of sweet spot in here in the green, where you're metal rich, but you're not too metal rich. You've had sufficient time to evolve life, but you're not so close to the inner regions of the galaxy to be permanently blatted by the supernovae. And you work this out, basically the really dark green is the favorable bit in this study, and you find that the sun lies quite close to that in this. So you've got this kind of sweet spot going back the very earliest, probably about 8 billion years ago, kind of here. about 7 kiloparsecs from the center of the galaxy, where this is maybe the sweet spot where life could really start getting going. And then that envelope kind of broadens out in terms of distance and time as well. Okay, so it's another bit is it's not only where you are in relation to the solar system or your star, but also maybe where you are in the galaxy that favors the formation of life. So what if we go off and we do find Earth too? So it's in the right bit of the galaxy. Some people don't really believe the galactic habitable zone, by the way, but maybe there's something in it. So in the right bit of the galaxy, the right distance from the star, what else might be involved that really difficult to kind of pick out scientifically? Well, there's these rare earth arguments out there. So things such as you don't really want to get hit by big rocks from space. So we know that the atmosphere, sorry, the Earth has been hit by big things in the past. You know, all these kind of examples of craters, and this is my favorite, of course, kind of 65 million years ago, dinosaurs were wiped out by probably a 6-kilometer wide asteroid. And I like to think that this is actually the face a T-Rex would have as the asteroid comes in. I suspect it's not what they did. Okay, so if you look back, this is actually a percentage of marine life destroyed in the Earth going back about 500 million years. You can see a bit alarmingly, it's almost every 50 million years, you see kind of 30, 40, 50% of life. You know, the dinosaurs being wiped out was not by any means the largest mass extinction event. You know, this one probably wiped out about half of life. And then you actually see pretty nasty going back 500 million years. It's like all the time 10-20% of life on Earth is getting hit by stuff, but then we sweep out all the nasty boulders. So there is this, that we're constantly being hit, less so now, which has probably given us a bit of a chance to get going. And one of the rare earth arguments is, well, maybe you need something like Jupiter further out, which we think might sweep up a lot of these comets and stuff that otherwise would come into the inner solar system and hit us. So there's a rare earth argument that not only is it temperature and where you are, but you need these other little bits and bobs to work in your favor. You need the demographics of the rest of the planetary system to work in your favor. In terms of this is just kind of, you know, you'll probably be aware of the Schumacher-Levy impacts. Some people actually think it goes the other way, and Jupiter actually scatters more asteroids towards us. So that, again, this is you know, kind of thing that not everyone agrees on. There's another thing, you know, the Earth has a very large satellite called the Moon, stabilizes our rotation. So Mars wobbles, so you get quite dramatic shifts in the seasons over its timeline. The Moon stabilizes the Earth's tilt, so it doesn't wobble all the time. So we have a pretty stable environment. It also generates tides, so that gives you a water-land interface. So, you know, my great-great-great-granddad was probably a fish that got swept up on a beach and then decided he needed to sprout legs and lungs in order to survive. You know, those kind of arguments. Another one is that you need an atmosphere, of course, but you need rotation. You need to have a magnetic field to protect you from solar flares. For example, so space weather, which you'll be aware of, you know, the northern lights and so on. If we didn't have these magnetic fields, we would be peppered by energetic particles from the sun, and that wouldn't be good for life in terms of the energetic particles aren't good for us, but also it can remove the atmosphere, and that's probably what's happened in Mars. Mars spins at the same rate, but it doesn't have a strong magnetic field in its atmosphere. Has probably been eroded by the solar weather with time. And that brings me back to this kind of classical habitable zone diagram as well, just to kind of give you an idea of things. So remember I talked earlier about when you get down to these cool stars, you've got this tidal locking. Okay, so a planet around here. So a lot of astrophysicists are looking for planets around here, for habitable planets here. Why? Because the orbiter period is about a week. They're a lot easier to detect because their orbiter period is really short. But they're going to be tidally locked, and they're going to be really close to the host star. Okay, we're in a 1 year orbit. These guys are 1 week orbit. They're right up against that host star. So for these kind of stars, there's a case of, okay, we've got a 1 day spin that generates the kind of dynamo that generates a magnetic field. It's like riding a bike with a dynamo light. The faster you spin, the brighter the light. Okay, if you lock your rotation period of your planet to the orbital period, you might be now looking at a rotation period of a week. That doesn't generate a strong enough dynamo to generate the magnetic field. So your magnetic field shuts down, and then you're really, really close to your host star. So you're right in the firing line of any flares that goes off. So maybe that atmosphere is just not going to survive very long around these cool stars. There's another thing, because it's tidally locked, you've got a permanent night side. Maybe what happens in the night side is it gets so cold down there, it causes the atmosphere to freeze out, and it causes the whole atmosphere to collapse globally. That could be another thing that rules out why these kind of habitable zones around these red dwarfs might not be habitable at all. And this is kind of a is that around these M dwarfs, around these red dwarfs, where that temperate or habitable zone is really, really close to the host star, M dwarfs crack out massive flares, really, really massive flares. Some of these, in terms of luminosity, they can brighten 1,000 times. If you imagine the sun got 1,000 times brighter, you know, forget that. Yeah, umbrella is not going to help you with that. And this plot is actually X-ray luminosity. So this is X-ray luminosity on a funny scale. So this dashed line here is the solar X-ray luminosity. And X-ray is really bad, likes to basically zap water. You don't want to be stood in front of X-rays. So the sun is down here. If I go from, say, this 6 to this 5, in these units, the X-ray luminosity has gone up 10 times. From 5 to 4, it's gone up 100 times. From 4 to 3, it's gone up 1,000 times. And these plots on here are the X-ray luminosities of red dwarf stars compared to the sun. So that's 10 times, 100 times, 1,000 times, 10,000 times the X-ray. Okay. Are these objects in the so-called habitable zone around red dwarfs really going to be a place where you're going to find life? I'll leave that for you. Here's another plot. You don't have to worry too much about this. I might actually just there for information, but also talked about the low mass stars, stars that are cooler than the sun. Okay, they're in the firing line of all that space weather from the red dwarfs. What about more massive stars? Well, more massive stars, so this is mass in solar masses. So the sun is about 1 solar mass, will last for about 10 billion years. Okay. If I go up to the most massive stars, they die really young. So this star here, okay, 17 times the mass of the sun, will only live about 3 million years. Not enough time to get life going. So if I put on kind of the life time scale on Earth, you know, we're up here, modern looking humans, that, you know, they're right up here. You can't plot it basically. Dinosaurs are pretty close to the top as well. Life kind of, you know, we've been around for about 5 billion years. Okay, if I have a look at kind of what we call an A0 star, okay, which is a fairly massive star, it dies at this point before life, even simple life, gets going. Okay, so even stars, you know, an F5, to give you an idea of that's a star that's not too dissimilar to the sun. If you looked at it, you would think it's not too different. It's a bit more massive. It's not that different. It would have died out by the time we get going, before dinosaurs get on the go. So the more massive stars, you've got a problem. Yeah, you can define a habitable zone, but they may not live long enough for life to actually get going. So that's why I've been interested in looking for Earth analogues, which is the opening piece, because I don't believe particularly that these cool stars are great places. They live a long time, but they may not be great places to go and find life. There's no point looking at the more massive stars, in my opinion, because they just don't live long enough. So this is just the final few slides. So The problem with Earth analogues is you're looking for something the size of the Earth, which is very small compared to the star. So all the effects that you're looking for, you can't go at the moment directly image one of these. It's too faint. They're incredibly difficult to find. You're looking for something in a 1-year orbit. It's incredibly difficult to do. But Kepler, which is this mission here, has shown us that we can actually detect Earth-sized planets. Remember that second slide I showed you? Kepler finds 100 Earth-sized planets. We can find them. We can find Earth-sized planets. Okay, and the way that we do this is we wait for the planet to cross in front of the face of the star. If the orbit is just in the right at the right angle, just edge on, we can see a little dip in the starlight as the planet goes across. It's very, very small. For the Earth, it would be a 0.01% dip in the sunlight if you viewed it as an alien, and that would happen once a year, and it would last 12 hours most, that dip, and then you'd have to wait a whole year and hopefully kind of capture a little dip again 365 days later, and it only lasts half a day if you're lucky. Kepler's actually shown that technically we can do this, and one of the missions that I'm involved in is the Plato, so it stands for Planetary Transits and Oscillations, and this is the first ever mission designed explicitly to find an Earth analog. Kepler wasn't designed for it. You might have heard of TESS. You may have seen things on the news. No other mission before is explicitly designed to find an Earth analog. So this is a 650 million euro mission, and that will launch around about 2026. So what I'm going to tell you, okay, it launches 2026. It'll take a bit of time to get going. At the most, at best, if we're lucky, we'll see a transit, and then we'll wait a year and we'll see another transit, and then we'll go, gotcha. Okay, at that point, we'll know that we've got an Earth-sized object in a 1-year orbit. So you could be looking at 2028, where we could go, we've got a candidate from this mission. There's a lot more work to do, but we'll have candidates if this works. Okay. There are other things that we've got to do. So the thing about this transit thing that Plato would do is it's going to tell you that you've got some object with an orbital period, and it gives you a little dip. So it gives you an idea of how big that planet is. But it doesn't tell us the mass of that planet. And annoyingly, nature likes to produce other things that produces dips like this as well. So what we want to do is we want to go and weigh that planet. Okay, if we've got the radius and we know how massive it is, you can get the density, and then you can say, oh, it's rocky, or it's gassy, or oh no, it's a complete what we call false positive. And I used to have to explain what false positive was, but that's where COVID has helped. Okay, when you actually go, that wasn't COVID, that was a false positive test result. We can get this with this as well. Plato will produce things that look like Earth analog dips, okay, but turn out to be something different. So to go off and really say, no, that was a true result, is we want to go and weigh that. And the way that we're doing that is looking at how, as the planet and star orbit the center of mass, what happens, the star wobbles back and forward. And we can measure that wobble with these kind of instruments. So Espresso can do this. So give you an idea of what we've got to do. If I was looking at the sun, and a new Earth was there, okay, so we could detect the transit of Earth, but I want to get the mass of Earth, so I can say it's rocky and it's real. What I have to do is I have to measure the sun moving by 10 centimeters per second. 10 centimeters per second. Okay, Usain Bolt does 100 meters in less than 10 seconds. So Usain Bolt travels at 10 meters per second. That's easy. Okay, I can easily measure a star moving at the velocity of Usain Bolt, hundreds of light years away now, 10 centimeters a second, until this instrument that's just gone on the sky recently was technologically beyond us. That is just becoming feasible technologically, but there are other challenges, and I could give you a whole other talk on this. So this is Espresso. There's another instrument called Hi-Res that's going to be put on the new next generation called, this is the European Extremely Large Telescope. So that last image, these are the very large telescopes. So these are 8-meter telescopes. You need all that light that you can get. This is kind of a 30-meter class telescope. So here are the very large telescopes, and here are the pyramids to scale. Okay, this is kind of $1 billion sat here that this instrument will plug in. That's the challenge that we've got in order to actually measure the mass of these. Give you an idea, this is the instrument. This is basically the camera. Okay, everything in blue and this is a camera. This is a camera the size of a kind of a 4-story house, bolted onto a telescope the size of the pyramids of Giza. Okay, huge amount of effort that we need to do this. And there's science that we've got to solve. Even if we can technologically do it, there's still scientific issues that we have in order to solve this. So Plato will give us a candidate, and we'll probably be looking at kind of 2028, maybe 2030. It might take us another 10 years to go, yep, we've got something. And then, of course, what you want to do, I've only got a few more slides. What you actually want to do is then probe that atmosphere, and that's a whole new level of complexity. You know, looking for biomarkers, you might want to look for water. So this is basically light directly now from the planet as a function of color, and what you see is things like carbon dioxide. It's a greenhouse gas that likes to absorb. So what you see is the light drops, because the carbon dioxide is basically blocking light at those particular wavelengths from escaping. So you'd be looking for things like carbon dioxide, water, ozone, things that, you know, well, these things wouldn't exist unless it was being replenished in some way. Either biologically, there's always a problem that geological things can come along and trip you up as well. So looking at these biomarkers is extremely difficult to do. There are other things, and I forgot to put this plot in. This is another complex plot, sorry, but trying to directly image ultimately these planets. So this is, up in this axis is how bright something is, and then this is wavelength. So down here, this is in the optical. Out here, this is the infrared, how it glows. And we've got some kind of plots in here, but what I just want to kind of show you is that this kind of plot is the Earth, and this is Venus, and you've got Jupiter kind of tucked in behind. If you go out at 10 microns and you have a look at this, Earth, believe it or not, you would think Jupiter would be really bright, wouldn't it? That would be the easiest thing to image if I was an alien looking back at the solar system. In actual fact, at 10 microns, the Earth is the brightest planet in the solar system. So if I was an alien, I'd seen a transit, which I could do, okay, and I measured its mass, I would then be going, oh, okay, I'll try and image that Earth would actually be the one that would stand out at this particular wavelength, because we're the brightest planet in the solar system. And we've had proposals to do this, but again, I want to give you an idea of the technical challenge that you have. I've got about 3 slides left, by the way. So this proposal is Darwin. Okay, so what Darwin was is, again, to go out and directly image an Earth-like planet of the nearest stars, and it could only work for the very nearest stars to the sun. We're not talking hundreds of light years, we're talking like 10, maybe 20 light years, so really our neighborhoods. And what you have here is you fly a flotilla of space probes with telescopes. Okay, you put that out by Jupiter. Why do you put it out by Jupiter? Because the inner solar system has lots of dust that glows at 10 microns in the infrared. Dust glows, it's warm. You want to get away from that dust. So you fly this out in Jupiter. This is called an interferometer. So the nice thing about an interferometer is, while the individual mirrors aren't particularly big, you get a resolution that's equivalent to having a mirror that is full size extent of this range. So you can fly these thousands of kilometers apart, okay? But it's technically really challenging. You've got to fly these in a perfect basically squadron, if you like. You know, it's like the red arrow's gone mental in order to keep these in the right position, otherwise the whole thing fails. At some point you've got to get that data back to Earth. And I'm going to tell you, this is real. the technical challenge of this. You'll probably know Newton's law: for every action is an opposite and equal reaction. Well, the actual action of broadcasting the data back to Earth pushes the flotilla out of alignment. Just sending the data. That's like texting someone and flying off in the opposite direction. Okay, that was the technical challenge that you have here. Okay, the transfer of data is actually an action, and that transfer of data was enough to push everything out of configuration. If they can get it to work, this is actually on the right, a simulation of what you would see. Okay, so you can see Earth, Venus, and Mars. You don't really pick up on Mercury, but this is the kind of thing that you see. And then if I go on, they were actually even able to see, this is for the Earth, in the simulations, if they get it to work, you see the light varying, and you'll see that this is basically going up and down in a one-day period. This is the Earth's rotation, and what you're seeing is the different land masses and cloud coverage. And they were actually able to do reconstruction from this. So this is what the Earth looks like, and from the data that they simulated that you could get from something like Darwin, you reconstruct something that looks like this, which would be pretty cool. So then my final slide. Okay, so where are we in the future? So this is the Drake equation, which is actually a bit of a terrible equation because there's horrible kind of interdependencies. But this is basically saying, right, what are the number of civilizations that we could possibly talk to in the galaxy, but you could extend it to the universe or whatever you want. And these numbers are basically that this is the rate of star formation, but you can say there's a number of stars you've got. So you've got the number of stars you've got, that's a big number. And then this is the fraction of those stars that have planets. So between 0 and 1, okay? So if no stars have planets, it's 0, game over, but we know that's not the case. And then the next one is of these systems that have planets, how many have Earth-like planets, for example? Of those planets, what fraction has life? Okay, of those planets that have life, what become intelligent? Of that decreasing fraction, how many produce a civilization, by which we mean are able to communicate? Okay, and then we multiply by the lifetime of that civilization, okay, and how long they're able to broadcast. So until probably, I would say, Kepler, so until 8 years ago, the only number that we knew was this number, for sure, which is how many stars there are, and it's a big number. Where have we advanced on this? Well, we now know this, and basically how many stars have got planets. That has ranged in the past from only the solar system exists, but we now have statistics, and I would say if we haven't found, and I showed you a plot where we hadn't found planets, but basically my feeling is if we haven't found a planet, it's not that there isn't a planet there, it's because we've not looked hard enough yet. That they're still hiding because we're not technologically capable to find a planet that is actually hiding in there. Okay, so I reckon every star probably has a planet if we look hard, hard and long enough. Okay, then what are we looking at here? Well, if every how many kind of, well, actually this is not number of Earth-like planets, this is number of planets in that system. Okay, well, if every system has a planet, then there must be a minimum of at least one planet per system. Okay, so we've got a big number. This is where we scientifically know we've got a big number multiplied by a number very close to 1, if not 1, multiplied by a number that has to be greater than 1. So we've now got to the point of really not knowing what's going on to basically saying planets are everywhere. Planets are everywhere. And we're migrating to this. What fraction of these planets may have life on them? I actually believe that we might get a handle on that by the time I'm looking like this. And I hope so. And that's really where my kind of research aim is. Okay, that's dot on in 1 hour, which is kind of what I timed. I'm going to stop there and hand over for any questions.
Chris, thank you very much. Once again, lots of information. Need to go away and think about a lot of things you've said. But for the time being, could you stop sharing your screen so we can see the usual suspects? So, ladies and gentlemen, as usual, a digital hand, please. Otherwise, wave at me, and I'll bring in people from the room. And straight away, Mick Nichols is in, like Flint. Mick, your question, please. Don't forget to unmute yourself.
And we've got questions in the chat, so we can get to them in the.
Yes, we'll get to those as well.
Cool.
Mick, your question, please.
As I said earlier, I was watching you on TV yesterday.
Sorry.
And you showed all those like exoplanets on a board, you know, the orbits and everything.
That's right. Yeah, I remember.
And Earth, our solar system, I believe, we're in top left-hand corner.
Yeah, I'm trying to remember.
Turned around and said, "We're the odd one out," because all the others were behaving like each other, and ours seemed perfect and uniform. That's my first point.
Mm-hmm.
The second point is, I think that Drake equation is well past its sell-by date, because as we all know, it doesn't take into account extinction levels. It doesn't take into account second-generation planets, which they think Earth's a second-generation planet. And I think it's just people clutching at straws, to be honest.
So yeah, so on the Drake equation, that's why I put that caution in there. From a science perspective, in terms of a nice, fairly easy, understandable way that you can communicate what, you know, the kind of different numbers, it does actually quite a good job. But my issue with it is a lot of these things in that equation, whether you believe the equation or not, is of the correct form, are actually all correlated with one another. So there's lots of dependencies. They're not independent from one another. So I would certainly agree with you from that, but I think it still has its place in terms of allowing people to get a broad concept of what's going on. Going back, I think you're referring to the Kepler orrery. I can't pronounce it.
That's
so these were all the discoveries that Kepler had of all the planetary systems, and what you see is you see lots of planet and multi-planet systems, but in really, really tight orbital configurations. So they all have short orbital periods, and the solar system, you know, does stand out from that. And that was that kind of something I alluded to earlier when I said a lot of people are looking around cool stars for things in the habitable zone, because you're only looking for planets that have orbital periods of 1 week. And the reason why you're doing that is if you're seeing a signal that repeats once a week, okay, first of all, for these stars, the star is a much lower mass relative to the planet. Okay, so if you put an Earth-like planet and you pop that around an M dwarf, it has a much bigger influence on the star, so it wobbles it around much more, so it's easier to spot because the effect is much bigger, and it's repeating much more rapidly. So if I was going to make a noise of the kind of signal you're looking for, it would go okay. But if you then go and take the same planet, the Earth, but you put it around a star, you'll get something that might go whoop, whoop, you know, it's a very small signal that then repeats for a year. So it's much easier. It's what we call bias, selection bias. All our discovery techniques are biased to finding preferentially big planets in short orbital periods around low mass stars, because that's where you get the biggest the biggest signals that we can detect. As we improve our technology, we can then push to longer period and smaller planets, which is where we're headed at the moment. So, but it's still the case that we do not know of another planetary system that looks like our solar system. So we're still, you know, we believe it's this bias in our detection methods, but we don't know. So we could still be an oddball, but we don't believe we are.
The other thing as well, I think it's interesting that you said you're looking for Earth-sized planets.
Yeah.
Because correct me if I'm wrong, if a planet 2 or 3 times the size of Earth has life on it, then would its respiratory system not have to develop different to ours to combat the 2 or 3 times the gravity trying to pump blood around its body?
Yeah, it could be. All depends on the kind of radius. So yeah, if it's 2 or 3 times the radius, you can tweak the mass. But you start doing funny things with the atmosphere. So at the moment, what we see in the distribution of planets, we see once you get up to a planet that's about 1.5 times the Earth radius, 50% bigger, you're basically getting to 50-50 chance that that planet will have a big fluffy atmosphere. So rather than it look like a terrestrial planet like the Earth, it looks like a mini Neptune. We actually call them. So we have these super Earths and mini Neptunes, and they kind of overlap. So at about 1.5 Earth radii, yeah, we've got 50-50 that it looks as though it may be terrestrial. We could be wrong, but it looks like it's a terrestrial planet. But 50% look like these mini Neptunes. Once you're up about 2 Earth radii, they're pretty much exclusively fluffy gas balls, so they may not be suitable for life unless you want to evoke something that can swim around in gas giant atmospheres.
Well, thank you. Thanks very much.
Thank you, Vic. I'm going to take a question from the room. Deputy.
Yeah,
Chair.
yes, what I was wondering, Kepler and these telescopes that detect transit, how do you know you're detecting a planet and not, say, a large sunspot? And a large sunspot on a star may be cyclic. I mean, the sun has an 11-year period. So, you know, how do you know you're detecting a planet?
Yeah,
sunspot?
Yeah, it's a lovely question. So so it's relatively easy actually. So this is the case where you have, I've got, you know, you've that's your star, and then you've got some planet that goes across. Okay, so I'm blurred. Okay, so typically for the Earth, if you're seeing an edge on, the maximum duration of that transit across the sun is 12 hours. So what happens, you don't see anything, and then you get a dip in the light, and then 12 hours later, it will move. If you have a spot, when the solar rotation period was actually 24 days, 27 days roughly viewed from here. So a spot takes 12 days to get across. Okay, so a spot will come on, it will then take 12 days, and you'll see the dip last for 12 days. So basically that spot, while it can give a dip of the correct depth, it will last way too long. Okay. You could evoke funny kind of you know, geometries, you know, maybe you're looking, you know, at some kind of high latitude feature, whatever, an inclined star. But again, you do get something a little bit different than what you would expect from a transiting planet. And also that the spot has a color dependency. So if you put kind of blue goggles on and you look at the sun in the blue, the spot appears really, really dark. If you go off to the infrared, the spot doesn't appear as dark, whereas the planet will just look like a black occulting, pretty much a black occulting disk, all different colors that you look at. So it's fairly easy to distinguish it. Where your question is brilliant is when you're trying to weigh the planet. And in that case, things like spots, they're actually the real problem we have, because what we're trying to do is look for that wobble of the star, and we do that by basically locating the center of light of that star. When you have a spot come on, that makes the kind of light center of the star shift around, if you like, and that injects noise in our measurements. So spots are actually a real problem for us when we're trying to measure the mass of the planet. And that's why I was saying, when I was pointing out these new big instruments, you know, that one that's 4 stories high, saying like technologically we can do it, but we have scientific problems we've got to overcome. It's things like spots that are actually the challenge for us to overcome, because they produce noise in those measurements. So not a problem for transits. You have to kind of filter them out a little bit, but they're not a showstopper. At the moment, they are a showstopper for measuring the mass of of the planet, and I can give you a whole talk on that because that's what I do.
Okay. All right. A question from the chat. VK would like some more information about the potential habitable belt in the galaxy and how it's identified. Is it based on the formation time or the rotation speed? Do they matter?
Rotation speed, not so much. Certainly, time of formation does. So the center of the galaxy that formed first, and as I was saying, those early generation stars are not metal enriched. Okay, so they form from material that doesn't have the heavy elements that you need to kind of, you know, use foams and stuff and rock that you can walk on. So at the center of the galaxy, you've basically got stars there, and material when the stars formed out of that don't have material that can form rocks. And you need that even for forming Jupiter. We believe you formed the rocky core first and then you accreted the gas later. So even the gas giants, we think really do need that rocky material to get them going in the first instance. So right in the center of the galaxy, they're the old stars that haven't been polluted by metals from supernovae from earlier generations of stars. So the center of the galaxy is probably out. And also that's where a lot of the supernovae first occurred. The supernovae go off in the center of the galaxy that pollutes increasingly the outer regions of our galaxy more and more with metal. So you can think of almost like a kind of a wave of increasing metallicity rippling out from the center of the galaxy, and also in time, because it takes time for that ripple of that polluting metals, if you like, to make its way out into the galaxy. And then you get just so far where, yeah, you might have the right ingredients, but you end up having things that are too metal rich or not enough time to actually form life. And that's really the key. There's kind of 4 key bits of the galactic habitability. As I was saying, some people just don't buy into the galactic habitability and think, it doesn't really matter. Okay, so it is something that's debated as to whether there is a habitable zone in the galaxy.
Okay.
Hopefully that answered it.
Hopefully. A question from me then. Planets around multiple star systems.
Yeah.
Are they finding many, and does it change your model of the habitable zone?
Yeah, so Kepler was the first, if I'm right, finding a planet around binary stars. So, and it was, again, it was a surprising discovery. So you can have, when you're talking about binary stars, you can have two different planetary configurations. So you can have a really close binary system. So the stars are looking right, and you can put it out here. Maybe I'll take my blur off. Can I take my blur off? So you can see my hand gestures. There we go. Okay, so we've got really tight binary, close in stars, and you put your planet outside of the binary system. Or you can have a star with a planet that goes around it, and then your binary star is out here. Okay, so in one case, your planet is outside of the binary system. In the other case, the planet is inside the binary system, if you like. And we initially thought that planets around the close binary would be quite unstable, but that was the first one that was found. So we know several. In fact, we actually know of Kepler found a few planets that technically would be in the habitable zone of these binary systems. So there certainly have been found. The ones where you have star with a planet and then a star further out, and this could be thousands of AU, not so much, and we believe that they actually might be the unstable ones. But what we find is nature just seems to be able to work out a way of building planets and popping them in orbits in places we didn't expect to find them. But yeah, certainly planets around binary systems are perfectly doable.
Thank you for that, Chris. Ian Hargraves.
Maybe muted.
Yes, I am muted. Sorry about that, Chris. Yeah, no, the question I had when you were talking about biomarkers,
Yeah,
is methane a biomarker at all?
it is potentially. The problem with methane is you probably know from Mars is you can also create it geologically as well. So that's the issue with methane. But certainly it would be something to look at. In fact, a lot of people say, well, you need, in actual fact, kind of that geology and plate tectonics, volcanoes to get life going as well. So even if the methane isn't being produced by life, it's telling you there's something interesting going on. One of the things I would say, if I saw methane in the atmosphere, it'd be like, well, actually, we have found methane. You get methane in hot Jupiter, so we do know of methane in atmospheres, but these are the hot Jupiters. But if it was a small planet, yeah, I'd be very interested in that, because you'd be like, well, how do you get methane in that small planet? But the issue of biosignatures, you might have seen that one, was it a couple of years ago, Venus, and I forget what it was. It was a very strange signal that they saw.
Yeah.
What was it? Can anyone remember? Phosphine. Yes, that's it. So there was this phosphine detection in Venus, which we believe was just an artifact of how they treated the data. But there's still a lot of work by astrobiologists to say, like, what are the viable biological indicators, smoking guns. So there's still quite a bit of work going on there, and there's probably biosignatures that we haven't thought about that maybe we should be looking for.
Thank you, Chris.
Thank you, Mick Nichols.
Yeah, I was just wondering about the space probes and the technology, what you were mentioning about detecting these exoplanets. Has it ever been used to try and detect the theoretical 9th planet in our solar system? Because they still say there's something out there, doesn't they, affecting the other planets and things?
Yeah, generally not in this case. So I wish I had the plot. So Kepler, for example, looked at a very small patch of the sky, no bigger than Cygnus. So it looked at about 150,000 stars in a very small patch. So it wasn't actually wide field at all. You just stared at a little bit of the galaxy, well, a cone of the galaxy, if you like. So it wouldn't have been the right thing for that. Plato, which I talked about, is much bigger field. Okay, because basically we're looking for bright stars, and bright stars are rare. There's more stars that are further away and they're dimmer. So that does get a large field, but again, it's not really kind of geared up for looking for these things, because it's geared up to look for bright things, whereas the 9th or 10th planet, if you're American, would just be too faint for that. But there are other ground-based surveys not geared for exoplanet science. So there's they've changed the name of it, but the Large Synoptic Survey Telescope, which does go deep. And it does do all sky, so it's genuinely wide field, and that would be the best kind of source to go and look for that. There's TESS, which also does strips. It does actually do the whole sky, but again, you'd be looking for the brighter objects. So they just tend, for the exoplanet stuff, we just don't go faint enough, because if they're too faint, we can't follow them up. We can't even get the masses. Kepler, for those who know the magnitude system, the limit of magnitude to get a mass is phenomenally difficult. You need something quite bright, and some of these objects that we've published, they're naked eye. You can there's stars out there that you can see with your eye, where we found we get the planets. So but there are these other ground-based survey telescopes that will do that. Good question.
Okay, Michael. So last question then, please. And we're going to go back to Mid-Kent and Ian Hargraves.
Yeah, it's thanks, Paul and Chris. It's not really a question. It's I just make the comment that several of our members at Mid Kent are taking part in the Exoclock project, which is to try and detect the transits of exoplanets. And there's 3 or 4 of us that are doing that at the moment with very sophisticated cameras, etc. And I thought they'd be on here tonight, but I know the professor that's leading that one, he couldn't make it tonight, unfortunately.
Okay, yeah. I mean, it's really, really useful actually, because you might think, oh, we can't play a role here, but you certainly can, because a lot of the things that we're interested, what we see is if you have another as yet undiscovered planet, I'm sure you know about this, and that may not be transiting, but what it can do is it can basically wobble that planet and cause the transit times to change. But you also get planets where their orbits are decaying. So the transit time, you predict the transit time, and it turns up a bit later. Sometimes it's a bit earlier. As professionals, as you know, we have limited time on these big telescopes, so we just can't get the time to monitor all these objects. That's where amateurs can play a really big role.
Yeah,
and I'm pretty sure that's probably what you're trying to do.
Yes, well, it's a European project, I think, being organised. And yeah, as I say, we're at the moment, the guy that's leading that for MSAS, he's got several different cameras that they're evaluating at the moment to see which one's the best to do it. But they are very high resolution cameras, and they are also very sensitive cameras as well. So yeah.
If you don't have big cameras, I'm involved with something called the Next Generation Transit Survey, which is it's a suite of 12 robotic 20-centimeter, I think they are, telescopes in Chile. And we started up a citizen science project, I think kind of October, November last year, because we got too much data.
Yeah.
And we use machine learning to try and pull out, candidate transits, but we know we're missing lots of planets. So we've popped this data. It's like the Zooniverse stuff.
Yes.
Thing and the planet hunters. So we also have a citizen science project that you can get involved with there if you if people are interested.
Yeah, have you got a website for that, Chris?
Yeah, I do, but I can't remember it all. But what I can do is I can ping an email to whoever was contacted me and just pop that in. We've got candidate planets already from that.
If you pass that information on to us, Chris,
definitely.
We'll forward it through to Ian.
Thank you. Thank you.
Ladies and gentlemen, I think we should let Chris get back to his celebrations.
I've got a third wine.
So that just leads me to ask you to give Chris Watson a big next for instance in Astronomical Society. Thank you. Thank you very much, Chris.
Thank you very much. Thank you. Bye.